Hi, my name is Igor Melnyk. I am one of the authors for the paper Semi-Markov switching vector autoregressive model-based anomaly detection in aviation systems. In this video, I would like to give you a short introduction to our work. So the main motivation behind our work is that in recent years there has been a significant increase in applications dealing with dynamic, high-dimensional data streams, and whose objective is to monitor behavior of the objects, discovering meaningful patterns, or detecting anomalous events. For example, in the domains such as aviation, healthcare, activity recognition, financial modeling, and many others, we're dealing with the data which evolves in time, has multiple parameters, and can be of mixed data type. For example, a mixture of discrete and continuous parameters. The question then becomes how to properly characterize interdependencies between multiple data streams, and how to design detection algorithms to identify patterns, trends, or anomalies. So in this work, we build a model to analyze such data using a dynamic Bayesian network representation. We call such a model Semi-Markov switching vector autoregressive model, and in short it can be called SMS-VAR. So this is a fully probabilistic representation in which the discrete data is modeled using a semi-Markov process, and continuous data is represented as autoregressive process. Then we use the SMS-VAR model to design a detection algorithm to monitor the data or identify anomalies. The main application of our work is in the aviation systems domain, where the main objective is to detect anomalies in the flights. We show that the proposed framework is efficient, can detect multiple anomalies, and outperforms current state-of-the-art approaches. In this figure, I show an example of the flight data and the proposed SMS-VAR representation for data modeling and anomaly detection. So here's the time series corresponding to a landing part of the flight. The top portion over here shows discrete data corresponding to several pilot switches, for example, thrust, altitude, autopilot, flight director, and so on. On the bottom over here, I show continuous part of data corresponding to some of the flight sensors, for example, altitude, pitch, air, speed, and so on. The model works as follows. So a combination of the flight switches act as indicator for a particular flight phase, which then determines the dynamic of aircraft for a certain period of time. Another combination of switches triggers the transition to another flight phase, determining aircraft's behavior for some other time duration, and this process continues throughout the rest of the flight. The flight phase, over here, shown in red, is not observed in data, and therefore is modeled as a latent parameter. The lower right plot shows an example of the aircraft's path as it descends from 10,000 feet over here to a runway here. The coloring shows the phases which the algorithm estimated while constructing the flight model. So in conclusion, if you're interested in this topic, I invite you to read our paper, where you can find details about the model and the anomaly detection algorithm. Thanks for watching.